In this lecture, we are going to define a stability condition in the frequency domain. In the same way we define a stability condition for temporal systems, here we are going to use the frequency response to derive a similar criterion to infer the stability of closed-loop systems based on the open-loop transfer function. This is called the Nyquist stability criterion, and it has many practical applications. One of the main advantages of the Nyquist stability criterion is to be able to infer the stability of the closed-loop system by simply looking at the open-loop transfer function, and even when the open-loop transfer function is unknown, because the transfer function can be derived from its frequency response determined experimentally. By the end of this lecture, we should be able to extend the concept of gain and phase, understand the Nyquist stability criterion, and determine the stability of a system based on its open-loop transfer function. There are many applications of Nyquist stability. Consider this example. We have a controller, an actuator, and a process. The actuator and the process transfer functions are known. By looking at the system's open-loop transfer function, using the Nyquist stability criterion, we can infer stability if this system is put in a unit feedback loop like this one. Based on the open-loop transfer function, we can infer stability of the closed-loop system without having to compute the closed-loop transfer function. Before you go into more details of the Nyquist stability criterion, it is important to review phase and gain. Any linear system can be characterized by its frequency response to a sinusoidal excitation. Consider the system g of s. If a function a sine of omega t is applied to it and in the input, the output of this system will also be a sinusoidal waveform, but at a different magnitude and with a phase shift. The magnitude of the output will be b. Notice that the frequency of the output is the same as the frequency of the input. The difference is that the magnitude has changed, and also now there is a phase shift between the input and the output. That phase shift is called the phase of the transfer function g of s. If we now take the magnitude of the output and divide that by the magnitude of the input, this is the magnitude of the function g of s at a given frequency omega. Both the phase and the magnitude are frequency dependent. Even when g of s is not known, g of s can be obtained by experimentally exciting g of s with a sinusoidal waveform and looking at the magnitude and the phase in the output at a range of frequencies. This was covered in the past lectures. Consider a generic transfer function g of s that is defined here as a gain k and a ratio of the product of different poles and different zeros. We can evaluate the gain of this transfer function at a given frequency by simply replacing s with the j omega. The gain of this transfer function is simply the magnitude of the transfer function, and the magnitude of this transfer function is the magnitude of this constant gain k times the product of the magnitude of all zeros divided by the product of the magnitude of all poles. Remember that by placing a point on the s-plane, the distance to the origin is the magnitude of that point or that polar zero, and the angle that it forms with respect to the real axis is the phase of that specific polar zero. Assume, for example, that this transfer function has one pole and one zero, as shown here. We can evaluate the magnitude of this transfer function when s equals to j omega by selecting the value of omega on the imaginary axis. It is then sufficient to connect this point to all poles and zeros and find the magnitude of all these vectors. Let's call this magnitude a and this magnitude here b. The magnitude of j omega at this specific frequency is simply the magnitude of all zeros, that is b, divided by the magnitude of all poles, a. If this transfer function had another zero, say around this point, and the magnitude of this vector would be c, then the magnitude of the transfer function would be b times c divided by a. If we now add a pole here, whose distance to that point is d, then the magnitude would be b times c divided by a times d. We can now look at the phase in the same way. By placing a pole on the s-plane, so here we have the imaginary and the real axis, this angle here is the phase of that individual polar zero. Theta is the inverse tangent of the imaginary part divided by the real part. The real or the imaginary component of this pole may be frequency dependent, which means that the phase of each polar zero is also frequency dependent. For a system composed of many poles and zeros, the phase is the sum of the angle of all zeros minus the sum of angle of all poles. Back to the same example we had before with one pole and one zero, we can identify these angles theta1 and theta2. The phase of the transfer function is theta1 minus theta2. If this transfer function had another zero around here, we can call this angle theta3, and say another pole around here, whose angle can be called theta4, then phi would be sum of the angle of all zeros, theta 1 plus theta 3, minus the sum of the angle of all poles, theta 2 plus theta 4. Now that the concept of phase and magnitude are clear, we can move on and try to establish the Nyquist stability criterion. To do that, we need to review 3 different concepts before we put them together to derive the Nyquist stability criterion. The first one is the conditions for open and closed loop stability. Consider the open loop transfer function here. We have a controller C of S and a process G of S. Generally, the process and the controller transfer functions are known. The controller is up to the designer to choose, and the process can be identified experimentally. Consider the input of the system to be X of S and the output is Y of S. Here we have the open loop transfer function of this system, which is simply G of S times X of S. We're going to call this open loop transfer function L of S, the line transfer function or loop transfer function. If you now close the loop in this unit feedback arrangement, then the transfer function Y of S over X of S is simply L of S divided by 1 plus L of S, which is exactly what we see here. And let's call that a transfer function T of S. The open loop transfer function is L of S and the closed loop transfer function is T of S. Having the transfer function, we can now define the open and closed loop stability conditions. For the open loop stability, if T or L of S is the open loop transfer function, then the necessary and sufficient condition for stability of the open loop system is that all poles of T of S, all poles of the open loop transfer function must be placed on the left side of the S-plane. That means all poles have a negative real part and all their exponentials then decay to 0. The system is then said to be stable. If you now are interested in the closed loop stability, we can go back to our transfer function. T of S is the transfer function, the closed loop transfer function, and the sufficient condition for stability is that 1 plus C times G has roots with negative real parts. That is, the roots of 1 plus C plus G have real parts that are located on the left side of the S-plane. 1 plus C of S times G of S equals to 0 is what we call the characteristic equation, which is the denominator of the transfer function. So you can say that a condition for stability is that the poles of the closed loop transfer function are placed on the left side of the S-plane, or the equivalent statement would be that the zeros of the characteristic equation must be located on the left side of the S-plane. Notice that the zeros of 1 plus C times G are the poles of T of S, the poles of the closed loop transfer function. Let's take one example here. Let's assume that C times G is S plus A times S plus B. The open loop system is stable provided that B is greater than 0, which means that all poles will lie on this side of the S-plane. If we now look at the closed loop system, the transfer function becomes S plus A divided by S plus B divided by 1 plus S plus A over S plus B, which can be simplified to S plus A over S plus B divided by S plus B plus S plus A divided by S plus B. This part of the transfer function is the characteristic equation, and this is the entire transfer function. So the stability condition can be stated as the closed loop transfer function must have poles with negative real parts, or the characteristic equation in blue must have zeros with negative real parts. So when dealing with the characteristic equation, we are now dealing with the zeros of the characteristic equation to assess stability of the closed loop system. The open loop transfer function G of S times C of S equals to S plus A plus B has a 0 at negative A and a pole at negative B. The characteristic equation of the closed loop transfer function in a unit feedback system that is given here S plus A plus S plus B divided by S plus B. Notice something interesting. The pole of the characteristic equation is the same as the open loop transfer function. The pole of the characteristic equation is the same as the pole of the open loop transfer function. The pole in both cases is S equals to negative B. The 0 of the characteristic equation is the pole of the closed loop transfer function. The 0 of the characteristic equation is the pole of the closed loop transfer function. So for closed loop stability, the zeros of the characteristic equation, that is the zeros of 1 plus C times G, must have negative real parts. We could also say that for closed loop stability, the poles of the closed loop transfer function must have negative real parts. These statements are equivalent. So that was the first concept that we needed out of 3. Now let's move on to the second concept. For the second concept, you need to identify a function mapping that will display the phase and magnitude of the transfer function in a graphical form. Consider this function h of s equals to s minus 2. How can we determine the location of zeros of h of s graphically? To do that, we are going to use a new domain. We're going to use the regular S-plane that has an imaginary and a real component, the same plane that we have been using since the beginning of the course. And now going to introduce a new one called the W-plane. The W-plane is a representation of the phase and magnitude of function h of s when points from the S-plane are taken, are input there, and then mapped in the W-plane. Let's start with the most obvious one. If you take s equals to 2, which is this point, and replace s equals to 2 in h of s becomes 2 minus 2 equals to 0. So in the W-plane, we have a point located at 0. So this clearly represents the 0 of the transfer function, because the phase is 0 and the magnitude is 0. We can continue this analysis and take other points from the S-plane and see where they end up. For example, 2 plus 2j. If we now evaluate h at 2 plus 2j, this is 2 plus 2j minus 2, which is simply 2j. So the equivalent point would be placed here. We'll see later this distance now represents the magnitude of the transfer function at this specific frequency. And this angle is the phase of the transfer function at that same frequency. We can now attempt another point, 1 plus 1j. h of s becomes 1 plus 1j minus 2. This is negative 1 plus j, which should be located around here. This again is the magnitude of the function, and this is the phase. Finally, we have s equals to negative j. And the magnitude of the transfer function when s equals to negative j is simply h of negative j equals to negative 2 minus j, around here. Based on the concept of phase and magnitude, we now know that this angle is the angle of the transfer function when this input frequency is given to it, and this distance a is the magnitude of the transfer function at that specific frequency. This concept is better explained using the Cauchy's argument principle. Consider this transfer function with 3 poles and 2 zeros, as shown here. To evaluate the phase and magnitude of the transfer function at a given frequency, it is sufficient to set s equals to j omega and specify the point on the S-plane at that specific frequency. So this is the imaginary axis. When s equals to j omega, this point is placed on the positive imaginary axis. And let's assume that this is the point of interest. This is the actual frequency given to the system. To find the phase and magnitude of the transfer function, we can now trace lines from each pole and each zero towards that input frequency, and now evaluate their phase and magnitude of each individual pole. Let's assume, for example, that the magnitude of this zero is z1. The magnitude of this zero here is z2. The magnitude of this pole is P1, here we have P2, and the third pole we have P3. The magnitude of the entire transfer function when subjected to this specific input frequency is Z1 times Z2 divided by P1 times P2 times P3. We can now do the same for the phase. If we identify the angle of each individual pole and zero, say this one here, let's call that theta 1. The angle of the other zero, we can call that theta 2. The angle of this pole, let's call this alpha 1. This pole would be alpha 2 and alpha 3. The phase of the entire transfer function is the sum of the angle of all zeros, that is theta 1 plus theta 2, minus the sum of angles of all poles, alpha 1, alpha 2, and alpha 3. Cauchy's argument principle states that if you now take our W-plane and represent this vector with this magnitude and this phase, let's assume that this point ends up here. So this is the phase phi, and this distance is z. This represents the phase and magnitude of the transfer function at that specific frequency. This would be equivalent to take the function h of s, replace h of s with j omega, where omega is the frequency at this specific point, calculate its phase and magnitude, and then plot this point there. To summarize Cauchy's argument principle, we can select an input point P in the S-plane that will typically lie on the imaginary axis if the input is a sinusoidal waveform. Draw the vectors from P to each zero and pole, as we see here, calculate the magnitude of each vector, and calculate the angle of each vector with respect to the real axis. Then the magnitude of the transfer function, or the gain of the transfer function, is the product of magnitude of zeros divided by the product of magnitude of all poles. The angle of the transfer function, or the phase of the transfer function, is simply the sum of angle of all zeros divided by the sum of angles of all poles. The angle of the transfer function, or the phase of the transfer function, is simply the sum of the angle of all zeros minus the sum of the angle of all poles, as shown here. If we now take the magnitude and phase, we can plot that as a vector in the w-plane, and in the w-plane, then this distance is the magnitude, and this angle is the phase. We can now take this approach one step further. Instead of considering single points, we can now consider a collection of points that will form a contour in the S-plane. We can take this example now. Here we have 2 poles and 2 zeros, and our point of interest is here. We can connect this point to all poles and all zeros, find the phase and magnitude of the transfer function that corresponds to that point, and plot that point on the w-plane. Now if you take this point and move it slightly along a certain line, we can create a contour, and if you draw a contour on the S-plane, we shall see a contour in the w-plane as well. If the contour on the S-plane goes clockwise, it must go clockwise on the w-plane under certain conditions. So for a contour in the S-plane, we'll see a contour on the w-plane. Now something very interesting occurs here, and it's the whole principle of Cauchy's argument principle and Nyquist stability criterion. Let's start with this point around gamma 2. The point of interest now is placed here. For that point of interest, we have all lines going from poles and zeros to that specific point. We are now going to take this point and make it do a loop around that random contour. It could be any contour, but the key here is that we have a closed loop contour. We may move this point, say, to this location. Now all these lines will change, and the angles of all these lines will also change. We can continue the process, move this point here. Now all the angles change again, and do that one more time here, and so on, until we go back to the original point. On the S-plane, we should see a contour as well. For each point on the W-plane, we have a point on the S-plane. Now let's see what happened to the phase of this poles and zero. Let's look at this first zero on top here. What happens to the phase? Remember that the phase is the angle that these lines will form with respect to the real axis. So what is happening here? We can clearly see that as the point in yellow does a full revolution around that contour, these angles here will increase and decrease, but will not do a full revolution. The angle goes to a maximum angle and back to the original point. It just oscillates back and forth as the yellow point moves around that contour. The angle of that zero oscillates but doesn't do a full revolution. The same can be said for all other zeros and all other poles. If you look at this zero here, we see that that angle follows the same behavior. It will oscillate, will go up and down as the yellow dot moves around the contour. The phase of that zero starts at a given point, goes up and down and back to the same point. It does not do a full revolution. The same will occur for the poles. We can then say that the net angle change of all poles and all zeros is zero. So the net angle change as we go around that contour of the transfer function itself is also zero. If the net angle of the transfer function is zero, the W-plane must display the same behavior. We will see a contour here, the equivalent contour, and this contour must also have a net angle change of zero. And this particular contour here would behave like that. If we trace points going from the origin to the contour as a point goes around that contour, we see the same behavior. We see that this angle goes up and down and back to where it started. And we can say that this will now give a net angle change of zero. What can we conclude with this? We can conclude that the corresponding contour in the W-plane cannot encircle the origin. If this contour encircled the origin, then it would do a full revolution and would have a net angle change of 360 degrees. Now let's look at the contour given by gamma 1. The contour given by gamma 1 has a zero inside. We are going to take this point of interest here and make the point do a full revolution around gamma 1 in the clockwise direction. If this is the point of interest, you can now connect this point to all poles and zero, same way we did before. When this point moves along the contour, such as here, we can recalculate all angles and all magnitudes. And we can now move the point there, same thing will happen. And we can continue this process until we are back to the starting point. Now let's analyze what is happening to the angle of each pole and each zero. This pole oscillates and goes back to where it started. This pole angle oscillates and goes back to where it started, same for the zero. Something interesting occurs with the zero that is inside of that contour. As the point moves along the contour, we see that the angle of this zero will follow that point and will not oscillate like the other poles and zeros. In fact, it will also do a full revolution of 360 degrees. Based on this, we can say that as the point moves along the contour, the net angle change of this transfer function is plus 360 degrees because of that zero inside of the contour. If we now go to the W plane, we shall see a contour that will display the same net angle change of 360 degrees. And by now you guessed, this contour must encircle the origin, like the one we have here. If this contour encircles the origin, for every point along the contour that comes from the S-plane, we see that the angle is increasing and eventually going back to the original point, but following a revolution of 360 degrees. So when you have a zero inside of the contour, we have one encirclement of the origin on the S-plane. To summarize, as S traverses gamma 2, the net angle change of phi here is 0 degrees. As S traverses gamma 1, the net angle change is plus 360 degrees. Where is this plus from? This is from a convention that clockwise rotations are positive, then this will result in a clockwise encirclement of the origin. If this contour had a pole inside, remember that at the phase of the transfer function is the sum of the angle of zeros minus the sum of angle of poles. So we have a negative sign, and the encirclement would be in the counterclockwise direction because of this negative sign. The net angle change would be negative 360 degrees if the contour had a pole inside instead of a zero. Now let's look at this example here. It is a very similar example, except that now we have a pole inside. And you see that the angle of all these poles and zeros that are outside of the contour will oscillate and go back to zero. But this is not the case for the pole that is inside here. The pole that is inside here will follow the 360 degree revolution, this point, and the net angle change will be 360 degrees. On the W plane, therefore, we should see a contour that encircles the origin once. So now, if we move along this contour, the angle change is also 360 degrees. Once again, the phase is the sum of angles of zeros minus the sum of angles of poles. This here is zero because they are all outside of the contour, and you're left with negative 360 degrees because we now have a pole. This means that on the S-plane, the encirclement will occur in the counterclockwise direction. Notice that here we go in the clockwise direction, and because we have a pole inside, the encirclement on the W plane goes in a counterclockwise direction. As S traverses gamma 1, the net angle change of phi here is negative 360 degrees. Now let's look at another example. Here we have this contour that encircles 3 zeros and 1 pole. The contour by definition is always given in the clockwise direction. What is the net angle change of phi? We have 3 zeros, so each zero inside of the contour will contribute with plus 360 degrees times 3. And each pole will contribute with negative 360 degrees. We have one pole inside of this contour. So the net angle change is 720 degrees. How do we get 720 degrees on the W plane? Well, we need two encirclements of the origin in the clockwise direction. So we should see a contour doing something like this. Each revolution around the origin is 360 degrees. So for two poles, more than a zero, we have plus 720 degrees, two revolutions around the origin. What happens if we define the contour here around these two poles? Well, then we should see two encirclements of the origin, and these encirclements will be in the counterclockwise direction because the net angle change would be negative 720 degrees. What happens if we define a contour around this zero and this pole? What happens if we define a contour around this pole and this zero? The net angle change is plus 360 degrees because of the zero and negative 360 degrees because of that pole. So the net angle change would be 0 degrees. And the contour here cannot encircle the origin. It will loop around like that, but it will not encircle the origin, and the net angle change of this value phi would be 0 degrees. Now let's assume that we had a contour here defined in the clockwise direction in a mysterious area of this S-plane in a way that we don't know what is inside of that contour. But if you look at the S-plane contour, we would see one encirclement of the origin, and this encirclement would be, say, in the counterclockwise direction. Can we say that this contour has one pole inside? No, we can say that the contour has one more pole than 0. In the same way that if we saw a contour in the clockwise direction, we could only say that the contour defined in the W plane has one more zeros than poles. What about a contour that doesn't encircle the origin at all? Can we say that the contour defined in the S-plane has no poles and no zeros inside? No, but we can say that the number of poles and zeros inside of that contour are equal. There is the same number of poles and zeros. Maybe there are no poles and no zeros, but you could also have 20 poles and 20 zeros, and the result would be the same. The principle we just discussed is implemented here in MATLAB. In this example, there is one pole in the S-plane, and the red contour is defined around it in the clockwise direction. We can see that as the contour goes clockwise, the contour on the W plane goes counterclockwise and encircles the origin once. This indicates a net angle change of negative 360 degrees. Now let's attempt the same example but with two poles inside of the red contour. Each pole contributes with negative 360 degrees to a total change of negative 720 degrees, or two encirclements of the origin in the W plane. So if you run this code, we should see two encirclements. There is one, and that's the second one. Now let's do the same with two poles and two zeros inside of the red contour. What should happen? Each pole adds 360 degrees, but each zero adds negative 360 degrees. The total angle change is 0. This means that the green contour in the W plane cannot encircle the origin. If you run the code, we see that an encirclement of all zeros and poles on the S plane results in that a green contour in the W plane, and the green contour does not encircle the origin. Finally, let's try this with three zeros. Each zero adds 360 degrees to a total of 1080 degrees, or three encirclements in the W plane. That's one encirclement, that's the second, and that's the third encirclement of the origin. Now before we move further, let me ask you a question. How would you use this principle to assess the stability of a given system or a given transfer function? Say you have a transfer function h of s. How would we assess the stability of h of s? How would you define a contour that would assess the stability of h of s? Well, if you're looking for the stability of h of s, we know that the poles of h of s will need to be placed on the left side of the S-plane. So a good choice for the contour would be a contour that encircles the entire unstable region. And if this contour that encircles the entire unstable region with a radius here that goes to infinity has poles or zeros inside, then you shall see encirclements of the origin on the other side, on the W plane. Of course, this does not guarantee stability because these encirclements could be due to the zeros of h of s, but what causes instability are actually the poles of h of s. So assuming that we know how many zeros h of s has inside this contour, we would be able to tell if these encirclements are coming from any pole that is also inside that contour and would make the system unstable. So assuming that the characteristic equation, now we are dealing again with the characteristic equation, so don't get this mixed up. We are dealing with the denominator of a transfer function, not h of s as we just saw. Let's assume that this transfer function has a number p of poles in the right half plane, a number p of unstable poles. Now let's further assume that this transfer function has a number z of zeros in the right half plane. If you now take a contour that encircles the entire unstable region, and if you know how many zeros and how many poles the characteristic equation has, we can now count the number of encirclements of the origin in the W plane, as the net number of encirclements would be the number of zeros minus the number of poles. The net number of clockwise encirclements of the origin is z minus p. And again, we are defining the contour at infinity that encircles the entire unstable region. Now, if this is the characteristic equation of a transfer function, what makes the system unstable? The system would be stable if you have zeros inside here. Remember that the zeros of the characteristic equation are the poles of the closed loop transfer function. Back to our example, where the open loop transfer function was s plus a divided by s plus b. If you put this in a unit feedback loop, we have s plus a divided by s plus b divided by 1 plus s plus a divided by s plus b, which is s plus a divided by s plus b divided by s plus b plus s plus a divided by s plus b. Here we have the entire transfer function, and here we have the characteristic equation of that transfer function. Notice that if we have zeros of the characteristic equation inside the unstable region, the zeros of the characteristic equation are the poles of the closed loop transfer function, and the entire system is unstable. But based on the number of encirclements, we cannot tell if these encirclements are coming from poles or zeros. And of course, if we have poles inside here, these poles will not make the system unstable because these poles are the poles of the characteristic equation. But what makes the system unstable are the zeros of the characteristic equation. Notice that this pole is the same as the open loop transfer function pole, which means that we will know how many poles are in here if we know the open loop transfer function. We also know the number of encirclements of 0, so we can now determine the number of unstable zeros inside of that contour. So this is a summary of exactly what we just discussed. A contour map of a complex function will encircle the origin n times, where n equals to z minus p. Z is the number of zeros inside of the unstable region, and p is the number of poles inside of that contour of any function. But in the case we are looking at a characteristic equation, then if there are any zeros inside of this contour, the system will be closed loop unstable. And once again, the number of poles inside of this contour are known from the open loop transfer function. Let's do this example. Assuming that there are no poles in the right half plane, so p equals to 0, are the following systems stable? So here we have their contour. Let's say we have the function 1 plus c plus g. We define the contour at infinity, input these points into this function, got an equivalent contour, and these are the 4 contours we see here. If the result is the first contour, is the closed loop system stable or unstable? The system would be stable because the number of poles is 0. We have n equals to z minus p. The number of encirclements is also 0, z minus p, which is 0, z equals to 0. The characteristic equation has no zeros in the unstable region. Same with this one, z is also 0. What about this one? This one here, we have one encirclement, n equals to 1. We again have no poles in the unstable region of the characteristic equation, so p equals to 0, n equals to z minus p, n equals to 1, z is what I want to determine, plus 0, z equals to 1. This characteristic equation has one unstable 0, and the closed loop system therefore has one unstable pole. The last one here, we see 2 encirclements of the origin, so n equals to 2. If you trace a line here from 0 to infinity and count how many times the contour crosses the line, n equals to 2. And you guessed the system is unstable as well, with 2 unstable poles, or the characteristic equation has 2 unstable zeros. Very well, now let's try to simplify this a little bit more. When looking at a unit feedback loop, we will always end up with a characteristic equation in the form of 1 plus the line transfer function, which in this case is c times g. If you are concerned with stability of this characteristic equation, then, based on the discussion we just had, we would need to watch for encirclements of 0. There is a small inconvenience with this problem, is that this characteristic equation needs to be calculated. We need to take the open loop transfer function, add 1 to it, and then look at the poles and zeros of this characteristic equation. This is a bit inconvenient because the zeros of the open loop transfer function are not necessarily the same as the zeros of the characteristic equation. How can you solve this issue? Well, we have this number 1 here that it could be removed if you subtract 1 from the entire expression. If you subtract 1, now we are dealing with c of s times g of s. What happens to the Nyquist contour? If you now take this contour and subtract 1 from it, the entire contour will shift to the left by 1 unit. Now, instead of looking at encirclements of 0, we are looking at encirclements of -1. So we have 2 choices. We take 1 plus c times g and look at encirclements of 0, or we subtract 1 from that expression. Now we are left with c times g. And you look now at encirclements of -1, because now the entire contour that we will now call Nyquist contour or Nyquist plot will shift to the left by a amount of -1 units. We can now say that if the open loop equation has a 0 or pole in the right half s-plane, the contour of this transfer function will encircle -1. The advantage here is very clear. We can now look at the open loop transfer function and infer stability of the closed loop system by looking at encirclements of -1 in the Nyquist plot. Now let's take the equation we just derived we can rearrange this expression as z equals to n plus p. If we now take an open loop function L of s and put this in a closed loop system, the open loop transfer function will have z closed loop unstable zeros given by z equals to n plus p, where n is the number of clockwise encirclements of -1 of the Nyquist plot, and p is the number of unstable poles of the open loop function L of s. If encirclements are in a counterclockwise direction, then n is negative. For stability, z must be strictly 0. This means that for every pole in the open loop transfer function, we must have one counterclockwise encirclement of -1 for the system to be stable. Counterclockwise because counterclockwise is negative. So if we have one unstable pole in the open loop transfer function, and the Nyquist plot displays one encirclement of -1 in the counterclockwise direction, then the closed loop transfer function has 0 unstable poles, or the characteristic equation of the closed loop transfer function has 0 unstable zeros. And here is the stability criterion. This is as simple as it gets. A open loop transfer function L of s is closed loop stable if and only if the number of counterclockwise encirclements of -1 is equal to the number of poles of L of s with positive real parts. Poles of L of s, poles of the open loop transfer function, and we are now assessing the closed loop stability based on the open loop transfer function. So for every unstable pole in the open loop transfer function, we must have one encirclement of -1 in the counterclockwise direction, so that z, the number of unstable zeros of the characteristic equation of the closed loop system, or the number of unstable poles of the transfer function of the closed loop system is 0, and the system is said to be stable. And this is the Nyquist stability criterion. We can look at an open loop system and immediately tell if that open loop system will be closed loop stable or unstable. This is the concept of Nyquist stability criterion, and it might be one of the hardest concepts in control system to grasp. So if the concepts here are not clear, I strongly recommend that you watch the lecture one more time. We'll do some exercises, but the exercises are extremely easy. This is the formula, and you all need to do here is to count the number of encirclements and number of poles. What is important beyond simply using or applying the Nyquist stability criterion is to understand what it means and how it was derived. So once again, if these concepts are not clear, do watch the lecture one more time before you attempt the exercises. Thank you.